This is lecture 13 of CS47 Computer Organization Study, and this part will start with Boolean algebra, which has been taught a little bit in the Math 42 in terms of logic manipulations and logic algebras. Before even we start, let me just put the foundation of this study, this half of the semester study, uh, and why, and let me try to explain why we are trying to do this. So we are now, after the midterm, we are shifting our gears towards understanding how things are done inside a processor. Okay, so far what we have been taught that how to program a microprocessor using a low level language like assembly, and we kind of get hold of that whole concept that there are basic instructions like arithmetic instructions, logical instructions, and also there are like decision making instruction to construct basic formation of any program and stuff like that. Now question become like how a processor actually execute those instructions, right? So this understanding of how a processor work is not is not fully covered in CS47, but it will be extended into our computer architecture study of CS147. So from this part onwards, these are kind of an stepping stones towards that understanding how given a microprocessor can execute this given instruction to them. Like for example, if I write an assembly program like add t0 t1 t2, how this microprocessor is going to actually perform that specific function. Okay, so that's the main subject in 147 along with some others as well. But to make that transition from CS47 to CS147 study, we are going to attempt to understand how things are done in terms of inside hardware for arithmetic logic unit. Okay, so we will be focusing especially on the arithmetic and logic unit, which is core of any computing system, because final target of any computing system is to be able to compute some arithmetic functions and some logical function. So let's first understand in this course how an ALU works, given that especially how an addition, subtraction, multiplication, division works inside hardwares, how it comes up with the result. Okay, so that's our target for this semester, that to understand how a computing system or an electronic device can perform these basic functions, arithmetic function like addition, subtraction, multiplication, and division. Now to understand that, first thing we all need to know that everything inside ALU, and that says everything inside the processor, are nothing but bunch of logical operations. Okay, so there is no fundamental add or subtract or division or multiplication operation, but there are only fundamental operations like an and, or, not, etc. Those kind of operation which are very much part of Boolean algebraic operations, they are only performed at the electronic device level. Okay, and combining those different Boolean algebraic function, logical algebraic functions, combining them, we start constructing more complicated logical devices to compute addition, to compute subtraction, to compute multiplication and divisions. So that means to understand how things are done inside ALU, arithmetic logic unit, we need to understand how the logical operations are done. And to understand that, we need to have a background of what are the logic operations, what are the properties of them, how they interact with each other, right? So that's what I would presume that you have been picked up from your Math 42. We'll review some of those skills in this lecture, Boolean Algebra 1, and in next lecture we'll switch to some specific methods and specific topics for the digital logical circuit implementation. Okay, so they are part of Boolean Algebra Study 2, which includes K-map and etc. We'll see that in that lecture. But this lecture, let's review what we have learned from Math 42, but we'll review it in terms of digital logic implementation. Okay, so what is digital logic implementation? Is how we are going to implement a logic circuit which can evaluate some basic arithmetic functions or some other logical function. In general, any logical function can be implemented with digital logic implementation, and their background concept goes in hand with logic algebras, and we call it in general as a Boolean algebra in digital logic implementation world. Okay, so that's the background. So we are going to, in nutshell, we are going to study how an arithmetic logic unit can perform addition, subtraction, multiplication, division on given values, right? Then to understand that, we need to understand how all those functions can be built up together by combining different logics, okay? And to understand these logic elements, okay, we need to first kind of understand or recap our experience with the logic algebra. Okay, so that's the whole background. So our topic would be quickly review Boolean values and operations, Boolean functions and truth tables, basic identities and algebraic manipulations. Okay, so to start with, this is very easy. As a recap, a Boolean variable assumes two values, true or false. Like any algebraic variable, right? It assumes like any values, like for any arithmetic values. It can be integer values, it can be real numbers, and so on and so forth. But Boolean algebras can take only two values. So a Boolean variable can take only two values, true and false. Now, true in our digital circuit world is represented as 1 and false is represented as 0. Okay, this is just a symbol. Okay, true. I think in the Math 42, most of you probably have done with symbolizing them as a T and F. Now, in the digital, since we are kind of studying this whole thing from the digital logic construction angle, digital circuit design aspect, we will be representing them as 1 for true and 0 for false. And there are three basic algebraic operations. One we call it AND, represented with dot. In Math 42, it was called a conjunction, represented with an caret, right? And OR we represent with a plus, and it was in the math world, it's called a disjunction, or represented with a V, right? And NOT we usually represent it with a tick, like a tick mark, like a tick means not of A. Sometimes we use a tilde operation, like tilde A is basically not A. Sometimes we use a plain, okay, exclamation mark followed by the variable name, that's also AND. So NOT has couple of different like generally accepted symbol for in the digital work. Okay? Most popular is a tick. Sometimes we go with a tilde, sometimes we go with the exclamation mark. In the math world, it's called a negation operation, and its symbol is shown in this slide. So I believe most of you are familiar with these operations: conjunction, disjunction, and negation. Now it's the time to switch over to think in terms of and, or, not, corresponding to conjunction, disjunction, and negation. Okay, so this is one switch you need to make in this class as a thought process.